Klingo system in the browser here again. I just start that. If we add a rule like that, it says, so Px holds if x is larger than 7. If we try to instantiate that, then we have a little problem here, because we can instantiate x by infinite number of different constants. So we are looking at numeric constants. So you could, for example, instantiate that by 1, which is possible. So if we replace that by 1, and we have to replace the same variable we did here, and then we see here, so we get a solution, but the solution is an empty answer because there is nothing in here, because 1 is not bigger than 7. So P1 is not a part of the solution. So it's satisfiable, but it's an empty answer. If we would replace the variable, so let's go back here. If we would have replaced the variable x by, let's say, 9, for example, and we run it again, then we see here that we have P9 as a solution in our model. And this happens because 9 is larger than 7, which is the comparison in the body of this rule. But if we have the rule in general, like we have seen before, then we have infinite many possible instantiations or replacements of x by any possible number. And at any time you create these kind of rules which have potentially infinite many instantiations, then we receive an error which is called an unsafe variable error. So here is a variable design which is, well, it can have infinite many solutions or infinite many instantiations, and this is impossible. So you have to be a little bit careful about these kind of rules. So this is the unsafe variable. It will occur in problems at times, and we have been, well, I then can, we can consider these things maybe in a little bit more detail. Okay, so far, maybe I return to my roadmap slide. So this has been the part about rules, and we next talk about a pooling statement, which is something quite simple. It's just an abbreviation for rules. So you remember we had this little database talking about the sizes of countries. Sometimes, well, it's a tedious job to specify these things in an ASP program, and somebody would like to do this in a more compact or in a shorter way, and this is possible, as you can see here in the last line here. So this is just an abbreviation of the same program as we see here, and it's quite easy to understand. So we have the size predicate, and we have always pairs of 2 parameters like France and 65, or Germany and 83, Italy and 61. And those pairs of parameters, they are separated by a semicolon, as you can see here. So this means just the same. If we just use this and put it into our Klingo system, so I just paste it to the input section, and if we then click the run symbol, then you see here that we have the same model as it has been provided before. So this is no difference. So this little program is the same as the program below. I could show that. If we run that, we don't get any different answer. It's, well, the idea behind this is simply it's an abbreviation for typing things. One can specify multiple predicates of the same predicate symbol with different sets of parameters. So in this case, these are just pairs, but they could be one parameter or three parameters or four. Then we have to specify one parameter or triple or tuples with four parameters. And those tuples have to be separated by a semicolon. Okay, so let's have a look at another small example. So as you remember, so this is a yellow box. It would be an example you could think about the problem by your own. So the question here is, there is a little program about some parent relationships, and could this be abbreviated by using a pooling statement? Well, yes, of course, this can be abbreviated by using a pooling statement. Going to show that. So we just have to specify the parameters just within one, one rule, one pooling rule about those persons. So if you run that one, you see here, it's just mimicking the input. And if we replace this, or if we replace this by semicolons, the program will look like that one. And this is a pooling statement. If we run that one, it's just the same, or we could just add more parameters like Bob and Fritz. And if we run that one, we get another Bob and Fritz. So this is the idea about pooling. Very, very simple. It's just a form of abbreviation, nothing else. Maybe let's have a look at that one. So this is also an exercise you could do on your own. So if you see this rule here, this is also a pooling rule. What would we expect to find in a model? Okay, it asks, so what stable model will this one produce? So any idea about that? And of course, we can try it in Klingo. Before I hit the button, just think about that. So what will it be then? Well, the pooling is with the semicolon, so it will say something like P12, then P24, P48, P816. If you run that, you see here, so we get these four separate predicates with two numbers as parameters. And of course, we could simply add some more of these, like 5, 6 or 16, 300, and more similar things. And you see here, we just get those additional predicates. Well, this is just an abbreviation, most simple. And well, it could be used as an input statement for well, some databases you would like to provide. Okay, so this was the very basic part about rules and pooling and getting started. And things like that. So the next part is about running Klingo, and well, I just pick some parts out of that, because running Klingo in general also talks about running Klingo from the command line and what has to be specified there. I will come back to that when well, at the time when I'm talking about running Klingo from the command line. But there are a couple of things which are interesting. So you probably know from other programming languages the term directive. So, well, most of the programming languages I know, they include something like directives. And directives normally are not parts of the programming language itself. These are just advisories to the interpreting system of the programming language. So if we look at our little problem about well, no, I just explained it to you. We are using this little program here, and this one has just 3 different P predicates. So let's have a look at that one. Well, it just reflects what we have introduced. Well, important fact about this little program is that those 3 P's, they are different. The first P is just a predicate P without any parameter, and this one is with just a single parameter. So if you would like to have multiple of them, we could use, for example, a pooling statement like PCD. And this one is about predicates that have 2 parameters, and we could also add a couple of things like that, maybe 3, 4, or comma T, and 6, 7. And if you run that program, then we see here we have a single predicate with just well, with no parameter at all. Then we have this P predicate with 1 parameter, so it's A, B, C, D, as you can see here. And then we have 4 predicates with 2 parameters, and these are those. Okay, so far, well, maybe just another interesting detail about this program, and maybe I just restructure my program here a little bit. Okay, so the new thing here is that we can add something like a show directive. No, not something like, we can add a show directive, which is shown here. And well, our model here is not too big at all. So it just consists of 8 predicates, P, PA, PC, PD, and so on. But eventually, these models can get quite large. If you have a big database and we have rules creating more atoms and things like that, then we might be interested to just have a look at an interesting part of the program. And here, for example, if we are just interested in those predicates with 1 parameter, then we can add a show with P/1. And if I run that one, you see here that we are just seeing those predicates here. And the show predicate, well, sorry, the show directive. So directives in Klingo start with a sharp sign, and then there's a space, and then there's a predicate name and a slash, and then the number of parameters of these predicates. So if I change this to p/2, then I will see only the predicates with 2 parameters. The show directive, it just gives you a part of the model, and just the part of the model which you are interested in. So you can select this part of the model which is most interesting for you, and you can have a specific look at different things. For example, if you remember the traveling salesperson problem, so there have been a lot of facts in the problem. So we have nodes, we had cost statements, we had something like connection statements. Well, we can have a look at that. You see here, there's the show cycle. As you remember, if I run that one, we just see the cycle here. But in fact, the overall solution is a model which is much larger. So if I remove the show cycle here, we see the complete model. And you see here, so there's the complete model, and this is quite large. And we have so cycle predicates in there, we have reached predicates in here, and we have cost predicates and things like that. And you can select any type of, using the show predicate, you can just select the parts of the model which you would like to see. For example, if you are interested in the cost statements, you see here, cost predicates have 3 parameters. We would have to add a 3 here. And if you run that one, we see those 3 solutions, but just the cost predicates which are contained in the model. So that's the idea about the show directive. Or if you would like to see the reached part, then we would have to specify reached. And since reached is a 1 parameter predicate, we would have to add the 1 here. And if I add this here, then we see here, well, reached 1, reached 2, and so on. So this reach predicate in this example, it just ensures that we have been traveling to each of those 6 cities. So that's the idea about this one. But we are coming back to the problem. I would like to show you just the show directive and what's able to do. So you can select parts of the model which you are interested in. And in more detail, if we have P predicates with multiple different sets of parameters, so P with no parameter is a different predicate than a P with 1 parameter and a P with 2 parameters. And you could also have with 3 or 4 or 5 or any number of parameters. And you can select the one which you're interested in. For example, if you would like to see just the predicate with no parameters, then we would specify P/0. And then we just see this P rule, which is specified up here. Okay, so that's the idea about the show directive. Okay, so first directive we see here. And again, the directive starts with a sharp sign and it has a name. So in this case, you can't just choose it. It's provided by Klingo. Klingo knows what to do about the show parameter, and then the show directive, and then you choose your predicate name together with the arity. So that's the name of the number of parameters, arity. Okay. So there is another directive, and the other directive is we can specify a value for a constant. So, well, in this case, it's just simple. There is just one constant, C0, and it's replaced by UK. And, well, let's think about a meaningful example for that. Yeah, well, maybe I just use our initial little country database. It's up here. Okay, I use that little program. So we have the size statements. I would like to have another instance of Klingon. So let's add that here. And we also have this rule. Okay. Here, there is the rule. And if you think about this rule, that there has been something like C0, then this, of course, is different, and it would, well, we wouldn't get any meaningful solution for that. It just says the database here. Well, we don't have any large countries because our rule now says that a country C is large if C has size S1 and a country 0 has size S2 and S1 is bigger than S2, but there is no country C0. And we would have to specify this, or we could specify this by using the constant directive. So where is it? So here is the constant directive, and we are going to use that one. If I add this to my little program here, it just says we replace any constant C0 by another constant UK. So this one is replaced by UK. And if I run that one, then you see that we also get these large statements as we have seen before. So this is very simple. You can just replace a constant by another constant. So that's the idea about that one. We are going to see this one. This will be used in some cases. For example, if you would like to calculate problems with numbers, then it's always a good idea, for example, to specify an upper bound to a problem. Like if you would like to calculate prime numbers, then we would like to specify that we would like to have prime numbers smaller than, I don't know, 1,000, 1 million, or something like that. So the constant is quite often used to specify these kind of boundaries for those problems. Or if we would like to have a traveling problem, so we would like to try to find a solution for, well, if we start for 100 cities and then increase the problem to 1,000 or 10,000 or 100,000 or things like that. So this is an application case for this constant directive. Okay, so that was the second directive. Let's see if we have more of those. Well, there's also an include statement. That's it about running Klingo. So the other things here, they are about running Klingo from the command line. So you see here, you could specify a constant also by an additional parameter in the command line option. And well, if you use Klingo, then we can include multiple files in that, and we are going to see this a little bit later. This makes sense in order to separate different parts of a program into different files, which then are used to calculate different Well, so this slide is about what we have done all the time right now. If you use Klingo from the web browser, then you see here there's an input window and there's an output window. And interesting is this button here. So I come back to that one. Well, probably not in this lesson, but quite sure I was in the next lesson. Okay, and so this is yet for more command line options. So if you would like to see all possible things which are supported by Klingo, you can specify the -help. So if there is somebody using that one, it will return you something like this here. Okay. Yes. Just another little section about running Klingo. We have seen two directives, one directive which is show directive and the other directive which is the constant directive or const directive. And we are going to use these things for our examples. Okay, so let's move on to the next little part here about arithmetic and intervals. Okay, so about arithmetic. Of course, well, like in all other programming languages so far, we can have something like arithmetic operators, like there's a plus and a minus and multiplication parameter and some division. And well, we have to talk about this division quite soon. So there is just an integer division and a rest division, so which is called modulo. We are going to see examples very soon. There's also an exponential function or exponentiation, which is using two asterisk symbols. And finally, as the last arithmetic operator, there's the absolute value, which is written as usually in mathematics, you just have the just bars in the beginning and in the end of the arithmetic term. There are also bitwise operators, but I am skipping them in my lesson. They are interesting if you try to calculate bit operations and things like that. So you don't have to care about those. I'm not using that in my lecture, and they are not appearing in any questions about well, in the exam, of course. So we are just talking about the arithmetic operators as you can see them above here. So just the four basic operations together with exponentiation and absolute value. So let's have a look at that. And there are a couple of rules using the arithmetic operations like that one. So it says n times n plus 41. And you can calculate that, I don't know, maybe. But in addition to this arithmetic operators like times, plus, we also introduce the dot token for intervals. But maybe I just start out to use this little rule and use it without the interval thingy here. Okay, now let's have another instance of our program. I would like to simplify that little rule a little, that rule a little bit. I make it larger. So if you have a rule like that, so this could be calculated easily. It says we have a Pn, comma, and n times n plus 41. And well, we add this P predicate to our model if n is equal to 0. So if you know that n is equal to 0, then we can calculate that one. So n times n, 0 times 0 is 0, of course, plus 0 is still 0, plus 41 is 41. Okay, so let's check that. And of course, we see here, so it says P0, 41. So the first parameter is just the 0, and the second parameter is the 41. Or if you would change that, for example, like if n is 3, then, well, of course, the first parameter will be n again, so which is 3 in this case. And then we see here n times n. So 3 times 3 is 9, plus n is 12, plus 41 should be 53, something like that. Okay, let's check that. Okay, it says 353. So this is how arithmetic is working, and you can have it at various places. Like, let's have a look at the other rule. Let's use that one. Just to see that this arithmetic could be used in a different way. So it's very similar in the beginning here. So we say that n times n plus 41, but it says, so we add the P predicate to our model if n plus 1 is 1. And we could also have the arithmetic operator here. And this is just the same as we have seen before. So it says n plus 1. So of course, this is identical to n is equal to 0, of course. But we can use it in that way, and this will produce just the same result as we have seen before. Okay, so we can use arithmetic operators at, at all positions where you can add terms as we have been specifying them in the last section. Or you, for example, could also add a thing like here, like we add something like -7. This is also possible. And then if you run that, then you see here the -7. So we can specify arithmetic operations in any places where we could add terms to our program. Okay, so far for arithmetic operators, and we are going to use them in the very near future, so they are not so complicated. So let's have a look at this little bit more complicated rule. And well, this one adds an interval. So the interval says that n is varying from 0 to 3. So we have all instances of n, one instance with 0, one instance with 1, one instance with 2, and one instance with 3. So this is just kind of a loop, or kind of, well, it's the interval from 0 to 3. So n can, or n varies from, or n is used from 0 to 3. And if we run this little program, then we see here we get multiple P predicates in our model. And well, we just get one solution for each of those elements of the interval. So the first element is 0. This results in the predicate P041. Then the next one is 1, which results in P143. And then we have 2 and 3, of course. Or you could add, well, even more of them. Let's say if you would have 20, then we get just more predicates of those. Okay, so this maybe is a little bit confusing. So why are we getting those multiple P elements here? Well, it's just because we are using the interval on the right-hand side of the rule. And this is, again, just an abbreviation. So you remember pooling? We have been talking about pooling before. Let's see, maybe I have some pooling. Yeah, that was our little program about pooling. I just removed the show part here again. And well, we specified something like P, A, semicolon, C, semicolon, D, semicolon. It's just an abbreviation that we do not need to specify all those predicates on our, well, explicitly one by one. And very similar, also an interval is an abbreviation that, well, saves us from specifying different things. So what is this abbreviating? So we could have different rules like that. And I'm going to show that to you. So this little program abbreviates this program here. One. So, okay. The program in line number 1 is identical to the program in line number 3 to 6. And we can just check that. I removed that one by introducing a comment symbol, so the percentage sign. So if you look at that one, we see here, so the model says P041, P143, 247, and so on. So if I add this one again and I remove the others, okay, so this is a little bit of typing work. Sorry, that one. And if I run that one, you see here we get the same the same solution. So there has been just a permutation of the predicates and their well, the series has changed, so it's just a permutation, but this is not a difference. So we are talking about logic, and it does not depend on whether one thing is written before the other one. It's just a model, and all things are equal, and it's just a set of those things. Okay, so in order to understand that one, as I explained, the interval, like pooling, is just an abbreviation. And if we have an interval on the right-hand side, it abbreviates this program, which is shown here, to just one line. So this is more helpful, and it abbreviates a bit more, or it saves you from typing more things as in the pooling case. Well, so let's have a look at, well, maybe let's have a look at this variant of the program. So if I just add that one, well, let's think a little bit about what's stated here. So we would like to add a P predicate to our model. And this is just the same arithmetic as we have seen before. So a Pn is n times n plus 41. And we add this one to our model if we have an n, and the n goes from -3 to +3. And in addition, we have another condition which says that n has to be larger than 0. Well, this is an abbreviation here. And in this case, it abbreviates more statements as we have seen before. So in the case you have seen just before, it was an abbreviation of 4 rules to 1. And in this case, it would be of 7 rules to 1, because we have the numbers from -3 to 3, which are seven numbers. So -3, -2, -1, 0, 1, 2, 3. So these are 7. But if you run that one, we see here we get the same solution as we have seen before. So let's have let's think about how this abbreviation works. So we start from -3, and then we have 7 instances, and it would be -2, -1, 0, 1, 2, and 3. So line number 1 is an abbreviation of lines 3 to 9. And we can think about them, well, in more detail. So you remember, we have been talking about instantiation at the end of last lecture. And we could even do a little bit more about that. If you see the rule in line number 3, we could say, so we know n is -3. So we can replace -3. We can replace n by -3. So, and instantiating that furthermore, it would mean that we replace n by that one and n by that one. And of course, any appearance of n here, and even there. And of course, we can replace this statement by the calculation. So -3 times -3 is 9. -3 is 6, plus 41 is 35. And then we have the rule, we add p -3 35 if -3 is gleich -3, which is the case, and if -3 is larger than or larger and equal than 0, but this is not the case. So we don't add -3 and 35 to our model, which is also not appearing here. So that's the basic idea about that. Okay, so this is about intervals. Intervals is just an abbreviation for more complicated rules. We are going to see more examples very soon. Yes, so this is an exercise again. Write a one-rule program. So we would like to have a, well, this in case is a one-rule program, but this is using pooling, as you remember. And we would like to have another one-rule program which replaces this program, but which is not using pooling. So what could we do here? Well, of course, we have to use, that's the idea behind this one. We have just seen intervals. So let's try to figure this out. So we have P here. So I just drop it into Klingo. And then we try to do different things. So we see here, it just says P1, 2, P2, 4, P4, 8, P8. P8, 16. So how could we replace that one in order to generate the same model as we've seen here before? And we would like to do this using an interval. So of course, well, any ideas? Well, let's start quite simple. So I just leave my program in line number 1 and I try to, well, we just start using a new program. So we see here that we have 4 predicates and I could try to do something with a Q, for example. So, well, we would use something like n equals interval from 1 to 4, something like that, and a dot in the end. And if I use the n here, so what will this one create? So it says we add qn to our model if n is out of the interval from 1 to 4. Any idea what this one will create? So we have learned about intervals just before.
It will create a sequence from Q1 to Q4, and then we can probably multiply by
wonderful.
2.
Yeah, perfect. Yeah, I created that one. Okay, so, well, this is not just that one, but it creates 4 predicates, and we could do something something similar. So let's try to get hold of the first parameter. So what could we do about that one? So it says we would like to have 1, 2, 4, and 8. So what could we do about that one?
Can we just list these numbers using comma? No?
Not using the interval concept here. So the interval concept is just well, giving you a range of numbers starting from 1 to 4. Or maybe I don't. I don't have the solution by myself, but we have to, well, we could just try to think about that. if we do something like, so let's just try to figure it out. So first idea would be to do something like n times n. So let's try that one. So we see here we get 1, 2, 3, 4. But this is not what we would like to have here. So any other idea? We could use 2 intervals. Let's try to do that one. No, I don't know. Well, no, I don't remember the solution to that. What is there? No, there is none. Okay, I have to think about that myself. Yeah, well, it's an exercise. Anybody an idea how to do that? The relationship is times 2, isn't it? So 2 times 2 is 4. 4 times. Okay. So the other way. So how about that one? Let's try this one. So we have 1, 2. Okay, so this starts correctly. We have 1, 2, but we don't have the 3, 6. We have to add the 8, 16. So how to do that one? Maybe I could try that one. Okay. Do I have an unsafe variable? Oh, that's not a good idea. That's not a good idea, yes. Well, we could add something. I don't remember the solution here, but we could add something like eliminating solutions. So I could do something like that one and specify that n is larger than 2, which is not very elegant. And n is smaller than 4, and n is larger than 4, and n is smaller than 8. No, this will not work. Well, as I do not remember the correct solution here, we could just eliminate those numbers. So we would like to have 1, 2, 4, and 8, and of course we can say that n has to be unequal to 3, and more of those, and this will work. So it's unequal to 5, unequal to 6, and unequal to 7. Well, that's not a very elegant program, of course, but it should give us exactly the same. So that would be a solution about that. As you can see here, so we have Q1, 2, and Q2, 4, Q4, 8, 8, 16. It's the same as the P things here. So it's just, and well, it's a solution to that exercise, and it gives us a one rule program, because this is just a one rule. It has a head and a body. It uses an interval here. And since I don't have a good idea at the moment how to do this in a more elegant way, I just eliminate, or I just specify that n does not have to be allowed to be those numbers which are not appearing here. And if you just replace those things by the p, then we have this program, and it's just the same as before, P1, P2, and so on. Okay, so, well, this could happen, of course. So this is an exercise. I've been thinking about that. I have found a solution, which is not the perfect solution for that one. You can think a little bit more about this little program, and maybe you find a more elegant solution to that one, which is shorter than the program I provided here. But this could happen. This is also the idea about answer set programming. So we can try things. You can just specify things. You can run your program and change your program, and then try things out and find out what you can do. And when you find a program which gives us a solution, then, well, you have you can just play around with that. So that's the basic idea. Okay, so more programs about intervals. You see here, well, we would like to generate some kind of models, and we have to specify other things. You could try to do similar programs as we have seen before. Well, maybe let's, okay, there is, there are more programs. You could try these by your own. Just try to figure out a program which is creating those models. Here are more programs like the one we have seen here. Though this is comparing intervals to pooling again. So these two programs, they are the same as the one you see here. So, well, the program in the line up here, this is just an abbreviation for that one, and this is the same abbreviation. Well, and this here is another abbreviation for this program. So all these three programs, they are identical. We are just using different abbreviations. So let's try that one. And this is different to the program we have seen before. Well, it's just generating, well, we are using the interval on the parameter of the P predicate, and it generates these different instances within the model. Okay. So here is another example, which is kind of used in a couple of programs we are going to see later on. So let's just use that one. So we have a square predicate, and it has two parameters, and each of those parameters is specified by an interval. And if we just run that, then we see here we have square 1, 1, square 1, 2, and so on. So this kind of program is used, for example, if you would like to have a grid system. So if you think about a chessboard, for example, so this kind of resembles a chessboard. You remember chessboards have 8, or they are of 8 times 8 squares. And if you just would like to have those 8 times 8 squares here, which are 64 overall, then you can specify these things, and it generates just 1 square predicate for each place where you could position a figure on a chessboard. So this is quite often used in order to generate things. Maybe I also go back to our traveling salesperson problem. So where is it? I think it was, oh, it was here. As you, well, no, you don't remember. But for example, in the traveling salesperson, you remember we had those 6 cities, and you could also create those six cities by using an interval statement. So it says we have the cities from 1 to 6. And well, this is used quite often in order to specify the basic parts of a problem solution. So in our case here, so this is about a chessboard, or for example, answer set programming. If you look at examples on the net about answer set programming, then answer set programming is quite often used to solve Sudoku problems. And then you have a board with 1 to 9, and you could specify things like that, which is Sudoku field. And this could take some numbers. So we have a field at position 1, 1, a field at position 1, 2, and so on. 9 times 9 of them. So you can also have a Sudoku field 9, 3. So this is just a handy abbreviation for all these kinds of things. Okay. So here's another interesting exercise. Well, let's have a look. Okay, so time is nearly gone. So let's have a look at that one. And this is the final slide about intervals. So as you can see here, then we are finished with intervals, arithmetic, pooling, and rules. And so the next section is about definitions. So let's have a look at that one. This is still interesting, and we can see a certain effect of this program. So I just write it in a different way. So we have P1 to 2 and 1 to 4. And if I run that program, then we see here, well, we get, let's count them, 1, 2, 3, 4, 6, 8, 10, 12 predicates. Well, why is this interesting? You can think a little bit about that. And in particular, if you just look at one rule, the first one, and if we generate that one, we see here we get 2, 4, 6, 8 P predicates. This is because the interval on the first parameter is from 1 to 2, and the interval on the second parameter is from 1 to 4. So since we are varying the first one with 2 numbers and the second one is 4 numbers, is 2 times 4, it's 8. And the same thing happens with the second rule. So if I run that one, we vary the first parameter from 1 to 4 and the second from 1 to 2. And it also results in 8 P predicates. However, if you use those two rules, so you would assume that you might get 16 entries in our model. However, we just get 12 entries in our model. So why is this the case? So, and I would like to stop here. And well, you could use this as an example or as a exercise for the next lesson. And I will start with this example in the beginning, and I would like to hear if you get an answer why we just have 12 entries in our model and not 16. So, well, even if each rule is contributing 8 predicates to our overall model. So any idea right now? Somebody?
Because there are duplicates.
Yeah, because there are doubles. Okay, yes, you already found out. There are a number of, well, it's from 1 to 2, no? If I specify this one, then they are identical and we just get 4 of them. And these are identical, and so it just gives us the same number. Of course, yes. So that's the solution about that. Okay, so thank you for today. And as you have seen here, we finished the first 4 parts of our roadmap, including intervals. And in our next lesson, we start with definitions, and we maybe will see choice rules as well next time. So thank you for, yes, of course. It's an online session. No, it's yes. So no, well, yeah. Thank you for the question. Of course. Normally, our lectures are online lectures, and in particular, next week will be an online lecture. I'm currently trying to figure out. I would like to come to the university. Well, let's see, something like 2 to 3 times during this semester. We don't have a lot of lectures because we are always doing a double lecture on each occurrence. And in principle, I would just have to do 1 a week. So it's just, well, if I would do it on a regular size, well, I started later on. So it would be a 2-hour lecture every 2 weeks. And so in general, we have something like 15 weeks a semester. So it's something like 8 lessons this semester. So the first one was in the lecture room, and this one is online. The next lesson will also be online. I would like to try to be 2 or 3 more times to be in Deggendorf, but I will always announce this beforehand. So you will, well, the principle is it's online, and I'm going to announce it when I'm available at the lecture room in Deggendorf. And I will write this in the iLearn system, and I will announce it beforehand at the lesson as I did it right now. So next week is online. Thanks. Maybe so some people were not able to access the online lecture. I have to try to figure it out. Maybe somebody who was not able to get into the lecture could write me an email. So I just try to figure out why this happened. Okay, so thank you for today.